guys for being here. Thank you for being Sledge. We are the Rocket Project. I am Brandon Hernandez. I am the general manager. I will be giving a brief background of the project and what our current mission is today. Prior to other missions or other years, other groups would be satisfied with purchasing a solid engine and then designing an airframe around that and just launch it for either a tournament or a hike goal that they have themselves or for research purposes, such as what sounding rockets are for. But I wanted to make this mission geared towards more of a practical purpose. So recently, recently as in the last few years, CubeSats have been a big thing for industry places, so like SpaceX, the aerospace company, Boeing. CubeSats are huge right now, and the delivery method for them have been constant. You would have to wait either 6 months to a year, spend $80,000 to a couple $100,000 just to get a ride on a vehicle that's going to be used for some other project. So it's not really geared towards CubeSats themselves. So why not make one for individual CubeSats? And the way we want to do this is, the way we're trying to do this is we just split our project up into 3 different aspects: the structures, avionics, and propulsion. And the delivery system will essentially be a way of using a Raccoon hoisting a rocket vehicle with your payload that has a active stabilization system to have a correct trajectory and with a high efficiency engine to get you to your orbit. So with that said, I would like to give Yuan the floor for structures.
For the structure teams, our goal is to develop a Raccoon delivery system. So we have 2 different versions of Raccoon. The first is the Raccoon that uses the solar balloon, and the second is the Raccoon that uses the helium balloon. The solar balloon version is the best choice because the extremely low cost and it's a simple structures. However, the use of the solar balloon is highly restricted by the area. The solar balloon requires a really high temperature gradient, which means it needs the area has a really low temperature and has a lot of sunshine. For example, the South Pole is the best place to use the solar balloon. In order to use the Raccoon in other areas, we also design a helium balloon version. This is our helium balloon version. Because we use a helium balloon, in order to carry a large payload, we need to use multiple balloons. The problem of using the multiple balloons is that we cannot make sure that each balloon has the equal buoyancy force, so the platform might tilt a little bit. So we design a gimbal system to make sure the launch tower is always facing up. And we also design a truss structures to reduce the stress in this carbon fiber tube. This tube is connected to the balloon, and this tube is very long. For this prototype too, the tube is like 8 feet long, but the diameter is only like 0.25 inches. So the minimum is very large. So this is our solar balloon design. The solar balloon design is very simple, just a single solar balloon and a launch tower. The reason of so we made the solar balloon by using a trash bag, and it only requires the sun to heat it up. So the launch cost of the solar balloon version is only the cost of trash bag and the rocket propeller. And we don't use the gimbal system because from our experiment, the gimbal system will make the single balloon system less stable. So this entire system only has a trash bag and a single launch tower, so which is very cheap. So this is our prototype test. So from this test, we have proved that the gimbal system can actually work, and the gimbal system can serve as a stable launch tower. And we also found a problem in this test. We have wrote a balloon size calculation code, but we have some error in the code, so the balloon cannot generate enough lift to carry the platform. So we need to add more balloons to carry the platform. So we also have to design a rocket for the prototype 2 in order to test the recovery and the flight control system. And in the future, we will design a large scale of Raccoon to carry a large payload and eventually launch a cube state. And from this year's project, we have learned that the 3D printing is a very powerful tool in prototyping. So we have designed like 6 versions of gimbal systems. We don't need to spend time to fabricate. We just need to change the CAD and print it out. And like this rocket, the nose cone and the transitional part is very hard to fabricate in the traditional method. So we just 3D print it and reproduce the carbon fiber.
Okay, so I'm the team lead for the avionics. As Brandon said, we're doing a active stabilization, and this is going to be used after the launch from the Raccoon, which Yuan has been working on. And the way we're going to implement this is by using actuated fin tips. You can kind of see here, there's some motors. There's another slide that shows it better, but there's motors with linkages that go back to the fin tips, and they will be actuated using control algorithms and microcontroller to implement that. Okay, on this slide you can see a little clearer on the back. This is an earlier version that we did. And initially we were going to go for a full roll pitch yaw control. And to simplify things and to be able to prove the concept of the fin design, we decided to focus on roll control first. So that's why we decided to add these tips. These parts the tips will actuate, but the bottom part is stationary, and that gives us our stability in pitch and yaw, so we can just focus on roll. And you can see here we started fabricating this semester. Okay, this slide, you can see the motors a little clearer. The motors, the servo motors are here, the electronics is up here, and they're actually the fins are actuated through the rods, which use centering rings as guides. Right now we're about 15 to 20% done with fabrication. We just started because the design work is very intricate in this iterative process. But in the near future, during the summer, we plan to launch. We still have to do the control laws and the programming and finish up whatever's left of the fabrication.
Alright, hey everyone, I'm Jesse, I'm the propulsion team lead, and just to stem off what Michael and Yuan talked about in terms of our launch platform, I was responsible for the lifting stage of our rocket system, and essentially this is UCI's first liquid rocket engine. It's meant to provide about 1,000 pounds of thrust, so enough to lift a small car. But the goal of this presentation was to really bring light to the lessons learned of our project, and it immediately became apparent when we were designing the liquid engine that there were some clear-cut government regulations that we had to face. And one of the first ones that we faced was ITAR, International Trafficking of Arms and Regulations. Essentially, it's a set of rules by the government and a bunch of other nations that define what's a military act and what's allowed for civilians like us. So when we initially designed the engine, it was utilizing kerosene and hydrogen peroxide. Unfortunately, hydrogen peroxide, anything over 80% grade, is regulated by the Army, so we don't have access to it. Another form of regulation was our launch mechanism, in that the act of transporting a satellite into space is a military act. So we were limited in terms of what we could design this engine around. Right now, as it stands, it's going to be a kerosene and LOX, a liquid oxygen-based engine, and it's only meant to achieve a maximum altitude of 80,000 feet. That's simply a consequence of the ITAR regulations that we face. So in terms of what we finished from the beginning of the year, we went through the ignition system, the injector plate, and the combustion chamber, as well as the nozzle, and all of that was designed in accordance to the ITAR regulations that were set forth. And as of today, we have the nozzle, combustion chamber, and the ignition system taken care of. All we have left to do is take care of the injector plate. So just to briefly go over lessons learned in terms of the injector plate design, we faced a lot of design constraints in terms of optimizing the overall design of the injector, in that theory doesn't always equate to the results that you want to see, and the only way you can get around that is actually practically testing this out. So what we're looking to do is fabricate this professionally and go out and carry out some cold flow tests. Essentially that means supply liquid oxygen or kerosene through it to try to determine the overall losses due to the flow through the injector. Future goals. So the goal of this engine was to become, the goal of this at least propulsion team's project was to become UCI's first liquid engine rocket. And more or less, we wanted to provide some data for our structures and our avionics team to design around and see if in fact see whether or not we were able to determine the 1,000-pound target that we had designed around. A major lesson learned was that we couldn't find access or easy access to machinability on campus, and we had to heavily rely on professional manufacturers. Outside of that, we still aim to really optimize the overall design of the engine and really try to shoot for a really cheap, affordable space launch system for CubeSats.
So to put it into perspective, the budget that we had was a major constraint for us. We have, you can see here, we've asked for over $4,000 of budget just to do these basic things that we wanted to, and we've been able to work within that range so far. Granted that we're not completely done with everything we want to do this year, but some of the issues that I just want to recap were a budget constraint, limited access to machining. A major thing was our facility. We've been moved around. Our lab that we get to use has been moved around 4 times in the last 2 years, and it's never stable. Sometimes we cannot even use it to fabricate things due to dust created when we actually work. Purchasing errors we've been through. The purchasing office has made errors and actually cost us money in the process. And also one big thing was a lack of a full-time mentor. We don't get a full-time professor to help us out. So the professor is chairman, and we don't want to bother with that. But one thing that I've learned as a lead for this is organization and communication is key. Every time or every other day, I ask my team leads, what have you done? What are you doing? What are we gonna do? And then the same thing with them. I hope they're asking their team members, what have you done? What are you doing? And what are you going to do? Just like as Terry has asked me, what have I done? What am I doing? And what am I going to do? So with that, thank you. Any questions?